Major funding for the Ring of Truth was provided by Polaroid Corporation.
For 50 years, we've been bringing art and science together to change the way people see the world. Polaroid.
Additional funding was provided by the Corporation for Public Broadcasting, Public Broadcasting Stations, National Science Foundation, Carnegie Corporation of New York, the Arthur Vining Davis Foundations.
The rocket's red glare, like all the colors that set fireworks apart from commonplace fire, comes from the ingredients of the burning materials. That link between light and substance has let us understand the architecture of the atom. The atomic fireworks are even more spectacular, I think, than the colors that streak the night sky. I can see them only in pitch darkness. You can see them through television only with special aids television camera, this night vision device, and a high-sensitivity video camera. They are faint, but they are marvels, because they directly connect our perception to atomic events. What were we looking at? The device is a remarkable device. It's marked with its date and signed. It was made nearly 100 years ago. Used as a kind of scientific toy. It was a wonder of the time. The fireworks are not spread on the sky, but on a tiny painted screen of a certain mineral pigment, not unlike the screen of a television set. Above it lies a small needle. But the key, of course, is that on the needle there has been placed a tiny sample of radium compound made by dipping that needle into a dilute solution and allowing it to dry. The sample is unweighably light and invisibly small. And yet from that radium come all the flashes we saw, about 100 a second, and they've been coming for 100 years without change. And that means about 1 trillion of them since this device was new. Nowadays, there are many amplifying aids to detect these events. It doesn't depend only on the human eye. This, if you like, is almost an ear. Of course, it is a Geiger counter with its associated electronics. Once again, there can be little doubt of the host of atoms that must be present in the sample, any sample, here disclosed by these special devices. They are numerous, remarkably numerous. They are tiny, for they must be to be so numerous. And the events in which they take part seem sudden, random, discrete. This is the nature of the atomic world. We propose to spend the rest of this hour showing more paths to an understanding of the atom. For no single way is in itself convincing. Some of those paths have been walked along for centuries by the craftsmen, and some of them are in the laboratories of the day. But altogether, they lead to a central point, the compelling conclusion that all matter is grainy and atomic. It was the craftsmen who mastered the remarkable properties that go with specific materials. They were the first to journey towards the atom. The goldsmiths slowly refined their craft to take advantage of what gold alone could do. The gold worker begins with molten metal, but gold, more than any other metal, can be easily worked while it is cold. Urban Billmeyer in Chicago makes gold leaf, modern master of an old way. The steel rolls will stretch and thin that gold bar to a length of ribbon in an hour of work. Listen, you can hear the changes in the metal almost as well as you can see them.
It's just the properties of gold. Gold is a fabulous metal. Its uses, there's just no end to the uses of real gold. It just has that peculiar property that it can be beaten thin. Comparative to other metals, it beats very easily. It stretches, maybe not as readily as a gold beater would like, but it does stretch. Gold will do things that other metals won't do. It can be used for anything without discoloring or tarnishing. It's just impervious almost to anything. It actually can be exposed to the elements for 50 years without any change whatsoever.
After close to 100,000 blows, the metal has become something without parallel. Gold leaf. A whole Bible whose pages were gold leaf would be no thicker than one single sheet of ordinary paper. Lillian Billmeyer handles it with the delicacy of a gentle breath. The artisans learned that what they could do with gold was sharply controlled by the purity of the metal. To secure pure gold, they had to sort it from baser materials. Here, scraps of gold mixed with base metals are to be purified. He begins by adding still more base matter, granules of lead. An ancient procedure of refining, the fire assay, will rid the gold of foreign matter. As the lead melts, it reacts with the air, and the fluid that forms dissolves the impurities of the now molten gold. The moment of completion comes almost without warning. The impurities have gone off into the air or been blotted up by the cupel. Left behind is a dark stain. The assay has sorted out this gleaming bead of precious metal. Now the gold can be taken into the long processes of the gold beater. Sorting pure gold from dross barely hints at the inner unseen nature of matter. There are stronger hints to be found at a sandy beach. A good beach is a wide and generous place. It is large compared to we who sit on it. If it is not large, it will not work like a beach. It will not respond to wind and water. That size is important. What we see at the beach could not be there in a tiny space. A pinch of sand is not a beach. But a beach is not a rocky platform either. It is mobile. We see it moving in wind and wave. There is no beach, I think, without these two scales, the wide expanse and the myriad repeated grains of sand that give it its actions. To look more intimately at sand as a substance, we need to take a much closer look with the aid of a magnifier. One look is persuasive. Yes, sand is one word, but this beach sand is not one stuff. I see black grains, pink grains, and clear and whitish grains under the lens. Here and there you can see how wind and waves have sorted the sand. One small area was strikingly white. Look at the magnified view. Close by, we found a different hue. We are creatures of the eye, and so we think it's quite natural to sort by size and color. It works, but there are many other ways of sorting. Here is a rather surprising one. It is a magnet, and indeed, the magnet tends to collect black grains. We have no reason to believe that the black grains that we sort by color are just the same ones that the magnet picks up. It may take only a fraction of them. And so our sorting is never perfect, never complete. We must try property after property until we're satisfied that a single sort would leave a single set of properties that all the grains would have in common. The world is like that too. Pure water has one flavor. Pure gold is admired by the craftsmen everywhere because it works so well in one single way. I think there is a deep hint in this behavior of the beach. The sand grains surely are not atoms, but the idea of sorting to a pure set resembles the world so much that I think it gives us the strongest of hints that within the world, indeed within every grain of sand, there is another graininess, the graininess of the atom. It's easy to divide beach sand into distinct, purified components. We recognized that the operation was a sorting, grain by grain. But when the assayer purified his gold in this little cupel, there's no trace of graininess anywhere. The metal has a beautiful, soft, lustrous texture. And yet, might it not be that at a scale too small for us to see, the two kinds of purification are really the same? Somehow, within gold, there are grains, atoms, that have been sorted by the processes of the assayer. I want to try another chemical sorting more familiar than the assay of gold. So I sought the help of a generous neighbor who was a celebrated applied biochemist.
Hi, I'm Julia Child. I'm doing a very special meal and cooking it just the way Phil has requested. And we've got a very colorful meal here, I think, with these beautiful fresh green beans and this bright orange squash and scallop potatoes, beautiful tenderloin steak, and a little mushroom sauce on top of it. I think I'll just finish that off with a little more green for color. And then here's a special Phil touch. I'm going to do it just the way he likes it. and that is a teaspoon of coarse salt right in the middle of the plate. And finally, this is the final Morrison touch, finishing it off in a special way in the oven. Now we're going to have what I think is one of the great desserts of all time, a soufflé Grand Marnier. That's an orange soufflé flavored with Grand Marnier orange liqueur. So I'm just going to put in little drops in there. And this is a good old white sauce base with egg yolks, perfectly beaten egg whites, and in they go. Some people pour the base into the egg whites, but I like to pour the egg whites over the base. And the folding is the most important part of the souffle, because you want to be sure that the egg whites get incorporated into the base. That's beautifully folded now into the souffle dish, which has been buttered and sugared. I'm not going to fill it too full, just about the top. And in it goes to the oven. It's a 400-degree oven, and I'm going to start it and let it watch it for about 20 minutes. I think that souffle ought to be done. Oh, it is done! It's perfect. It's just perfect. Look at that. Soufflé Grand Marnier Morrison. That's just exactly what he ordered. Very happy it turned out so well. Now let's see the main course. I think that turned out very well too. Nothing like being an experienced chef in these matters. Look at that. A meal fit for a king. There you are, Professor Morrison. This is Julia Child. Bon appetit.
Julia was able to produce a similar black layer over the surface of half a dozen distinct foodstuffs. Well, to be sure, it didn't take all her artistry to burn foods. We can all do that. But there is something remarkable in the consequence. Whatever we eat is an ore of carbon. Salt is an exception, and water too, of course. And I think you will agree that they play somewhat specialized roles in our nutrition. That result, that a single component can be extracted as part of a great many related source substances, is one of the foundations or understanding of the atom. The chemists became convinced that everything they could try could be separated out, dare I say sorted, into a small variety of specific substances, a list whose names we know: carbon, gold, silver, lead, oxygen. Those substances, there were fewer than 100 of them, could not in turn be broken down by any treatment the chemists could muster. They were the best sorted grains of the chemist, and a class of sorted grains is what we call a chemical element. Let us try to take a well-known material and break it into its elementary constituents. We can sort water into two substances with an electrical current. The current enters the base of one tube and leaves by the other. Tiny bubbles form and rise within each tube to sum up into a noticeable space. Hydrogen on the left, oxygen on the right. Note the proportions of the two gas volumes. Before our eyes, the famous formula is realized. 2 volumes of hydrogen to 1 of oxygen, H2O. Something internal must be behind this simplicity. We did nothing to build in a simple ratio. Let's try the reverse, combining the two elements. The steel cylinders hold commercial hydrogen and oxygen. We put equal amounts of each gas into a single strong glass tube. That's the hydrogen. It displaces some of the water that was in the tube. 2 units. Now for the oxygen. The gases combined when triggered by an electrical spark. Watch again in slow motion. None of the gas escapes from the bottom of the tube. The newly made water just joins what was there. But there is something left over. There is always something left over. We tried all afternoon to change that result, but the gases were stubborn. Two hydrogens can take up one oxygen, but no more. One oxygen is left over. Something deep within water appears to know a little arithmetic. I do not claim there is only one way to explain so simple a result. But if there are atoms, and if within water they do cling into little clusters of the right type, that would explain everything very neatly. H2O. This gemmy treasure has been hidden from every human eye for much longer than human history altogether. We found it at a hammer blow. Such little earths, geodes they are called, are full of beautifully formed crystals. Those are entirely natural faces, just as they grew, a process that may have taken millions of years. But with magnification, we see crystals grow out of what appears to be nothing, a clear solution. The tiny gems with their gleaming facets all show strong family resemblance. They are evidence for an inner geometry in alum, as there was an inner arithmetic in water. These crystals of alum are the ones we saw grow under the microscope. They are about the size of fine table salt. A different substance, Epsom salts, grows elegant long needles inside a drop of its solution. Each material has its own inner geometry. Here are members of another crystal family, the commonplace mineral iron pyrites. These cubes are natural forms. The expression of the internal nature of pyrites is to make cubes and less orderly forms that are closely related to cubes. There is a graininess in matter, somehow, that wants to come out to express itself in the external form. There is cubical order in humbler crystals yet. Table salt. But the cubes are too small to see without magnification. There is a nice pyrites crystal that is not a cube, but it has cubical nature. It is this 8-sided figure, an octahedron. In fact, its 6 points fit very nearly into a cube. Once again, the 8-sided octahedron is not an exclusive with pyrites. Besides these common minerals, we thought we would bring a less common one to look at. This is a natural diamond. It does not have the many facets of the engagement ring, which are cut carefully by the lapidary. That's the way it grew. Of course, a diamond is diamond-shaped.
Look at what we have here, a diamond. How long is it going to take to cook this delicious object?
Well, we have to heat it to over 3,000 degrees Fahrenheit for about 2.5 hours.
Well, remember that recipe. 1 carat diamond, 2.5 hours, 3,000 degrees.
You can just place the diamond right on the pedestal.
Just looks like a home oven.
That's perfect. The diamond has to be cooked at extremely low pressures.
Well, this is a vacuum oven, and that's pumping the air out of the oven. I can see that very clearly. It is beginning to cook. It's turned a kind of a golden color. Well, I guess that's coming along nicely. Well, Trish, is it ready?
Would you like to see it?
I certainly would. Look at that diamond, that beautiful old diamond. That's just nothing but a lot of black powder. It's hard to believe, isn't it, that that little thing should be turned back into black dust. That's all there is to it. That looks kind of like a miniature burned souffle. I think it's a very sad sight.
All that is left of our gem diamond is here in this char. It resembles very much the charcoals we got from foodstuff. Another crude test might be made. I'm going to draw with diamond charcoal. So, a nice diamond streak. Haven't done that before. And just to compare, let me take a piece of burned string bean, also charcoal. Well, I got a bigger piece, but I think you will agree that the two are very much the same by this crude but quite interesting test. The furnace that Julia Child used was a vacuum furnace. There was no air for the diamond to take up. Had air been present, the white-hot diamond would have burned to make gaseous carbon dioxide, just as the carbon in the food we eat is oxidized internally and exhaled with our breath. But if you use the vacuum furnace and seal it up, take care not to lose anything, you can recover the full weight of the diamond in charcoal. But there's a difference between diamond and charcoal. They're not the same thing, as an effort to buy either one will show you. What can that difference be? The atoms are there, and they're the same atoms, and not much was lost. The difference must be in their geometrical arrangement. Diamond is a special pattern of carbon atoms, and sufficiently heated, they regroup to form another pattern, the more familiar one of charcoal. The clue we got from the crystals that showed the geometrical habit of atoms was valid. If atoms exist in patterns in space, we should somehow be able to measure their size.
I think I'm going to ready to make noodle right now.
We approach the division of matter by the attractive process of halving and halving and halving it again.
Okay. 1 time becomes 2 noodles. 2 times becomes 4 noodles. 3, double. 10. 11. 12. That is 4,096 strand. Look at that. Wow.
12 foldings produced 4,096 fine noodles.
Yeah.
And if Chef Mark could have stretched the dough 30 more times, the noodles would have reached atomic thickness.
That's called dragon spare noodles, like a human here. It's very fine.
A simple outdoors experiment allows us to see how thin we can get matter to be. We've chosen a pleasantly breezy day at the banks of a pond. Okay, looks good. Our equipment couldn't be simpler. Some olive oil and a set of measuring spoons. 1/4 teaspoon goes onto the water. The oil spreads of its own accord. As it thins beyond visibility, the oil remains detectable by the action of the wind. The wind ruffles the water where there is no oil film, but where oil is present, the surface is more mirror-like. The oil film spread, first fast and then very slowly, and then it seemed to come to a stop. And I would reckon that the area it covered was about 10 yards by 20 yards, or 200 square yards. Now, a square yard is 3 feet by 3 feet, so about 10 square feet. A physicist's arithmetic should not be more precise than his eyeball measurements. And that would give us about 2,000 square feet of film. The 2,000 square feet came from a spoonful less than an inch across. The oil film grew 1,000,000 times larger than the spoon. It must also have grown 1,000,000 times thinner. So I would say that the film we're looking at is, on average, when it stops spreading, about 1/5,000,000th of an inch thick. That's 100 or 200 times thinner than the gold beaters make their gold leaf, and it's a great deal smaller than Chef Mark's wonderful way of drawing out fine noodles. It's not yet the size of an atom. Oil is not just atoms, it's a complicated compound. But it must have some cluster of atoms, and we know that that little cluster, whatever it will be, is not bigger than a 5,000,000th part of an inch. Certainly, atoms are no larger than the thickness of the final film of oil. We are close to knowing the size of an atom. The results of our simple experiment are given credence by one of the world's most powerful magnifiers. At Arizona State University, David Smith and John Wheatley focus the beam of their transmission electron microscope on a familiar material.
In this case, our sample is a small sample of gold, very small particles of gold, and we put them on a small carbon film.
Well, the magnification on the monitor is presently about 30 million times.
The dot of an eye magnified this much would cover Greater Boston. We need to magnify millions of times to see atomic dimensions.
And as you can see, the individual alignment of the atoms we call lattice spacing or lattice fringes. And you can see the dark rows of atoms.
Each one of those black spots are these little rows of gold atoms.
And the little white areas would be...
Well, that's just holes in the lattice.
So we're seeing spaces between the atoms.
For hundreds of years, people have believed that atoms, maybe there were little discrete things that made up compounds and metals, and that they were different. Once you can see atoms, you can see how atoms stack together. And that gives us a much better insight into the properties of these materials. And the thing is that once we've got a video system attached to the microscope, we can start watching the atoms move around.
The modern electron microscope can image so tiny a speck of gold that we see the individual atoms, not one by one, but in a complex regular order. It isn't easy to interpret what we are seeing. Maybe some help is given in this way. It is not meant to be a precise model, but it is simply a wire model of some geometrical regular form. And as I move it back and forth, I have a strong sense of orderly packing. And every once in a while, as if by chance, a simple view, as though a whole array lined up at once, a whole column of marchers became as one. But when you do view the simple line, it's inescapable to think that at least the size of those marchers can be measured when they're all one image of one blocking the one behind. And that size turned out to be about a couple of dozen times smaller than the thickness of an oil film upon water. We knew that the oil film was larger than a single atom because a unit of oil is a cluster of atoms. Until the powerful instrumentation of our own century, No experiment that led to the atom was by itself single and conclusive, I think. But the fascinating part was that each experiment that pointed to the atom pointed to the same atom, the same in size, the same in number, the same in the simplicity at the heart of matter. Now, to learn how the tiny atoms behave, we turn to the study of fire and light. Darkness is the place to study fire. I have struck an ordinary highway flare, a kind of slow-burning firework whose characteristic color means danger on the highway. The eye can pick up that color from quite a distance, yet the color is surely a sign of the composition of the substance which is burning. So the eye can judge material from a great distance. That's remarkable enough. But we can do better than that. If we place before the single eye of the camera a device called an optical grating, slip it directly in front of the lens, we'll see something quite remarkable. The single flame has many partners dancing in the air like the flame of which they are images, are a series, an array of colored flames, all clearly dependent, flickering and moving with the flame itself. That is what the grating has done, separate the light by its intrinsic qualities into a series of images, no longer one on top of the other, as the eye must judge them and find a kind of sum, but instead in different places, plainer to see, perhaps. The second flare is of a contrasting greenish color. If you compare the spectra when the two are well lined up, you may see several little green flames from the green flare that are not present in the red. We have found a way to analyze the nature of a light source by a careful look at its color. Of course, the method is not restricted only to these flares. Out in the wide world, many light sources have distinct arrays of color spectrum to go with them. Every light source in Boston has its spectrum. They differ, just as the colors differ to the eye. When we look through the optical grating, we see more than meets the eye. Often there is a structure to the spectrum. In every pattern is written the physical nature of the luminous substance. This powerful source of light is the heart of a rather familiar kind of street lamp. The brilliant light makes a strong spectrum, and the individual images, of course, carry the shape of the lamp itself. If we can do so much out in the field, it comes as no surprise to learn that when they took this technology of spectra into the laboratory, it became the most powerful tool for the study of atomic matter. Before any atom can give off light, it must first gain energy. The hot gas flames excite the atoms we put into the flame, chosen because a few specks of those elements are enough to make bright color. Familiar red neon, mercury, hydrogen. Electrical energy, too, can excite the atomic colors. A few grains of table salt, sodium chloride, give the yellow flame, a good match to our small version of a highway sodium lamp. This spectroscope extends our sense of color. The narrow slit admits a line of light. The prism arrays that light, according to color, into many colored lines. I see a close pair of yellow lines, only a bony skeleton of the rainbow. A particular pattern of colored lines identifies an element. The spectrum is as good as a fingerprint, recording the colors emitted by a host of atoms all alike. Look at 4 fingerprints. These widely spaced lines were a puzzle for a long time. The physicists tried to match them with some internal state of the atom, a line for each state, rather like the notes of the piano. It just did not work. Finally, they had a surprising new idea. We can follow it by imagining a simple atom, really only a toy. Think of the toy atom with 3 energy levels, only 3 energy states in which it can exist. The lowest level is its resting state. First, let it gain energy to go up to the next higher state. When it drops back again, it gives off light. The energy the light carries off is the difference between start and finish. Every jump makes light of a particular color. Arranged in rainbow order, those colors are the spectrum of the toy atom. There is a tight match between the spectral lines and the energy level differences. That is the heart of the theory of atomic behavior we call the quantum theory. Watch once more. 3 energy levels. 3 transitions. 3 lines in the spectrum. Each line is related to 2 levels, the beginning and the end of every atomic process. And only with those energy differences can we get any fit with experiment. There is a possible test here. If the toy atoms were struck so gently that they never gained enough energy to go past the middle level, the spectrum would have only 1 single line. Can a real spectrum be taken apart? We will try to dissect a real atomic spectrum by controlling the energy that excites the atoms. Violet to 0. Here is the scalpel for that task, made by my colleague at MIT, John King, and his student, Scott Seleska. Could you turn on the light source, Scott?
Okay.
I think I can recognize in that eerie blue glow a color akin to that of the mercury vapor street lamp that we've seen before, and whose spectrum we did, in fact, examine. To make light, we normally crowd a lot of energy in, making the atoms collide as they will. But here we have another objective, and we'll exercise very close control over the energy that any atom can pick up. We do that electrically through this control. The higher we set it, the higher the maximum energy that any atom gets. To begin, I'm going to give it a good deal of energy so that we'll see that the system can produce the normal many-line spectrum that we saw from the street lamp. The spectral lines are plotted as peaks. A yellow and a green line in blue and violet. But the recorder pen kept going beyond the violet to note many lines invisible to me. They are ultraviolet lines, easily picked up by our electronic eye. And finally, a very strong line in the far ultraviolet. And that's the limit of our device. That's a pretty recognizable fingerprint spectrum. If we compared it peak for peak with the line from the street lamp, you could see very well that they were the same. When I place a more strict control on the energy of collisions, a quite remarkable response will follow. Now for the test. We started by feeding in no energy at all to see if we got what we could expect. It has to jump above this baseline if it sees anything. Nothing. Okay, good. All right, I'm just going to set it up. As we raised the energy setting, we raised the starting location of the pen to keep the record clear. The trace simply followed a higher baseline. Not a thing, not a piece of spectrum. So though we put in some energy and stirred him up, it wasn't enough. Look back at the toy atom. When we excite an atom only part way to its first level, it simply ignores the energy offered. Atoms make no compromises. It is all or nothing for them. All right, I'm going to try another jump. Well, not much yet. We got something. That's right. We've just crossed a step, right? That's a little bit of that UV line. I'll mark where that is. And at that place, one line of the spectrum comes on, yeah. This is a one-line spectrum of Mercury. That's right. We've dissected it down to one line. What about if I increase it and see if we get any more lines? And there it goes. Yellow and green. And those blues, violets, and the UV, plenty of those. We have spoken of atomic spectra very reasonably, as people thought about them for 100 years, as though they were something like fingerprints, there or absent. The fingerprint of Mercury is the Mercury spectrum. The discovery, the fact that that was not true, but that the spectrum has a physical structure, we can dissect it, we can reveal it line by line, was the outcome of this experiment many years ago. Even our experiment with a rather coarse energy probe shows that, I think. We found 3 distinct energies where the Mercury spectrum changed. No line, then one line only, then finally the entire fingerprint. With sharper control, we might have found 10 or a dozen steps on the energy ladder of Mercury. With the map, we can see how the whole spectrum is produced. That first large jump made the strong line far in the ultraviolet. The smaller jumps make lines whose color we can see. The energies of the levels can be measured electrically, and the light by its place in the spectrum. The excellent fit between the jumps and the colors was the triumph of the quantum theory. That deep discontinuity, not chaotic, but neatly matched to what happens with energy, is the real meaning of the quantum jump, which is no proverb or metaphor or slogan, but in fact expresses the behavior of the atoms that make up ourselves and all the matter in the world. The tones of the marimba change by steps, recalling the discrete energy jumps of the atom. The slide of the trombone can glide wherever it will. But if the marimba had 1 million closely spaced bars, do you think we would notice the gaps? The quantum jumps that are so conspicuous at the scale of the atom have not disappeared in our world of smooth change. They are there, but unnoticeable. Atoms are simply too small and too strange to be visualized in space as though we were looking at them. We cannot do that. But the quantum ladder gives the key to their behavior, and it can be used in many ways to manipulate and arrange them as we see fit. An old dream of all who sought the atom has been fulfilled. We will see one isolated, real atom in natural color. The 2 laser beams that stab the darkness are probes for this Seattle research group around Professor Hans Stamelt.
It has been known for a long time that atoms have colors. They can have very gaudy colors. In fact, the color of atoms is related to their structure.
Here is the local map we need, a small part of the energy level diagram of barium. The colors emitted as the barium jumps among these 3 states are nearly matched by the 2 lasers. The laser beams cross paths within an electrical atom trap no larger than the eye of a needle. Some barium is sent into the vacuum. The caught atoms slowly escape. The experimenters monitor the faint light from the barium until at last the signal tells them only 1 ion remains.
You use a laser which must be tuned to the atom. In the case of the barium ion, the color of the laser is blue-green.
Just the color that atom is able to pick up.
Now this ion should look bluish-green. And so it is quite correct to think of a barium ion, well, as a little blue-green dot.
This extraordinary photograph shows 1 single atom. It was taken with an ordinary camera. The atom is nearly still in space and viewed by its own light. It appears here a mere colorful dot. But what could you expect? Atomic detail simply cannot be disclosed by any light the eye can see. It was the deep knowledge of the energy levels of this atom, its quantum ladder, which enabled the experimenters to get almost absolute control to the point where they can count ordinary atoms 1 by 1 until a single trembling specimen was left to pose and be recorded by its own particular color through 1 million quantum jumps. 1 single atom. The quantum craftsmen have reached the ultimate in purity. The understanding of atomic behavior that is mapped by the energy ladders explains how atoms take up and give off definite amounts of energy. They can interact and yet return unchanged to their previous states, ready to perform again exactly as before. The quantum ladder leads to a world where atoms have specific and lasting properties that nevertheless are not eternal. That is our world, the real world, where gold glitters and yet can be melted, where diamonds are hard and yet can be burned. In a world of being and becoming, quantum theory is the first theory of matter, rich enough to accommodate everything we have found so far. I believe it is a permanent part of our knowledge, for ours is a quantum world.
Major funding for the Ring of Truth was provided by Polaroid Corporation.
For 50 years, we've been bringing art and science together to change the way people see the world. Polaroid.
Additional funding was provided by the Corporation for Public Broadcasting, public broadcasting stations, National Science Foundation, Carnegie Corporation of New York, the Arthur Vining Davis Foundations. The Ring of Truth book can be ordered direct by calling 1-800-441-3000. Have your credit card ready. Video cassettes for schools, colleges, and individuals can be purchased by calling 1-800-424-7963. The book, 1-800-441-3000. Cassettes, 1-800-424-7963.